You ever look at your phone or your laptop and just wonder what's going on inside? I mean, how do these tiny little squares of silicon actually power our entire world? Well, today, we're going to peel back the layers on one of the most complex, most fascinating manufacturing processes on the planet. Let's demystify the incredible journey of a microchip, all the way from a simple idea to a real piece of silicon.
First things first, let's just start with a fact that absolutely blows my mind every time I think about it. Modern microchips, right, often no bigger than your fingernail, are packed with billions of transistors. Billions! That's more tiny switches on a single chip than there are people in many countries. And these are the microscopic engines that run everything. And getting them to work together is just a monumental feat of engineering.
So, how is this even possible? Well, the magic behind cramming all that power into such a tiny space is called Very Large-Scale Integration, or VLSI for short. It's the whole field dedicated to creating these incredibly dense circuits. And you know what? To make sense of it all, we're going to use one simple analogy for this entire explainer.
This right here is the key. Building a microchip is a lot like building a skyscraper, and we're going to follow this path exactly. We'll start with the architect's digital blueprint, then we'll move to the engineer's super detailed construction plan, and finally, we'll watch our silicon skyscraper get built layer by microscopic layer.
Okay, let's start at the very beginning. This is the front-end process. Think of this as the architectural design phase. Before a single piece of silicon is touched, engineers have to dream up exactly what this chip is supposed to do. They define its entire personality, its functionality, all in the digital world. The heart of this phase is something called RTL, or Register Transfer Level Design. Now, this is where engineers are essentially writing code. But here's the twist. They're not creating software. They're describing hardware. They're using a special language to define all the logic, all the pathways for data. They're literally programming the chip's brain before it even exists.
Now, what's really fascinating here is that there are two crucial roles in this digital stage. You have your design engineers, they're the architects, the ones creating that blueprint. But then, just as important, you have the verification engineers. They're the inspectors. Their entire job is to stress test the design, throw every possible scenario at it, and hunt down every single bug before it goes any further. It's a critical partnership.
So once that digital blueprint is verified and totally bug-free, we get to move from the world of architecture into the world of construction. This is called the back-end process, and it's where we create the incredibly detailed physical plan for our silicon skyscraper.
Physical design is all about taking that abstract code and translating it into a concrete, geometric layout. Think of it as the structural engineer taking the architect's beautiful vision and turning it into a schematic that the construction crew can actually build. This isn't just a drawing, it's a super precise plan that shows where every single transistor and wire will go.
And this process is incredibly structured. It starts with floor planning. That's like deciding where the different departments go in our skyscraper. Then you've got placement, which is about positioning every single office, or in this case, the basic logic building blocks called standard cells. Then comes clock tree synthesis, which is all about making sure the building's heartbeat, the clock signal, reaches every single room at the exact same time. And finally, routing. This is like installing all the plumbing and wiring, connecting everything together with millions of tiny metal wires.
Now hold on. Before we break ground and spend millions of dollars on manufacturing, we have to be absolutely positively certain that our construction plan is flawless. And this is where a really specialized, super critical type of testing comes into play.
Right? That is the billion-dollar question. I mean, think about it. A single tiny flaw in this physical layout could make the entire batch of chips completely useless. So, over the years, engineers have developed some incredibly clever ways to bake testability right into the design from the very beginning.
The first strategy is called Design for Testability, or DFT, and it's all about being proactive. Instead of waiting till the end to figure out how to test it, you design the chip to be testable from day one. It's like an architect designing a skyscraper with built-in inspection hatches and diagnostic ports, making it way easier to check the building's integrity later.
Then you've got BIST, or built-in self-test, which is even cooler. This is like giving our skyscraper its own internal team of robotic maintenance crews. These are actual circuits on the chip whose only job is to run diagnostics and report back if they find any problems. The chip can literally test itself. How cool is that?
And finally, there's the really smart part, automatic test pattern generation, or ATPG. Instead of a human trying to guess every single thing that could go wrong, you have these sophisticated algorithms that analyze the chip's layout and automatically generate the perfect set of tests.
They're designed to find very specific physical faults, like a wire being broken or two wires accidentally touching.
All right, the blueprints are done. The plans are verified. Everything's perfect. Now for the grand finale, the physical construction. We're heading into the clean room to see how this digital dream becomes a silicon reality.
It all starts right here, with a perfectly polished, perfectly pure wafer of silicon. This shiny disk is basically our pristine plot of land, where hundreds, sometimes thousands, of our identical silicon skyscrapers are all going to be built at the exact same time.
The absolute core of the fabrication process is something called photolithography. The best way to think about it is like an ultra-advanced printing press. You shine a special kind of light through a mask, which is our blueprint, to project and then etch the patterns of the transistors onto the wafer. And this happens over and over and over again, building the chip up one atomic layer at a time.
So once all the transistors are formed, they're just sitting there, not connected to anything. That's where metallization comes in. Super thin layers of metal, usually copper, are laid down across the wafer and then etched away to create this impossibly dense network of wires, connecting everything and finally bringing the whole circuit to life.
And there you have it. What began as just lines of code, a purely logical idea in an engineer's mind, has been transformed into a physical device with billions of interconnected components. It's this tiny, powerful engine, now ready to be packaged up and put inside the devices we use every single day.
So what does all this mean if you're thinking about a career in this field? Well, this table breaks it down beautifully. If you love coding, abstraction, and pure logical problem solving, then that front-end role as an RTL design engineer might be perfect for you. But if you're fascinated by the puzzle of turning that logic into a real, physical, efficient layout, then a back-end role in physical design could be your calling. As you can see, both are incredibly challenging and, very rewarding fields to be in.
Which brings us back to our skyscraper one last time. This whole journey needs two totally distinct but equally brilliant kinds of minds. So it really makes you think, doesn't it? Which role is more fascinating to you? The architect who dreams up what the building can do, or the engineer who bends the laws of physics to actually build it?